Okay, Algebra 2 students, since we are able to now post some new stuff online, I'm going to start in on our Chapter 7. None of this is for a grade right now. I don't know, it probably will never be for a grade, but some of this will definitely come in handy if you guys are going on to trig or college algebra. So this is section 7.1. We are talking about sequences. Now, a sequence is a pattern, for lack of a better term, and we're talking about sequence of numbers that have a pattern. Maybe I should say that. In our vocab here, it says a function whose domain is a set of consecutive integers. The domain typically starts with a 1. Okay, so the domain is obviously, remember, your input. Okay, so you are given a rule. Okay, a rule is kind of like the, how you get the pattern. And then you're using the input numbers, and it's the counting numbers or the natural numbers that begin with 1. So we're talking about positive integers, essentially starting with 1. So 1, 2, 3, 4, those are your domain, that's your input. And then you're using that number somewhere in the rule to get to the next number. We've got two different types of sequences. We've got a finite sequence that has a particular beginning and an end. And then we have an infinite sequence. Those are the ones that end with the ellipses, the dot, dot, dot. That keep going on. So for instance, a rule may be, let me see if I can, it would be like 2n. Okay, so here's what we would say. We would say a to the n, okay, this just is telling us for any term, okay, that was the other thing in here. Each individual piece or each individual number of a sequence is called a term. So each term, we are taking the number, the input, okay, and multiplying it by 2. So our sequence would look something like, if we start with the number 1, it'd be 2 times 1, and then 2 times 2, and then 2 times 3, and then 2 times 4, dot, dot, dot. Okay, so this would be my sequence. Okay, again, this right here is my rule. Okay, that's how I get from one number to the next in my sequence. But that's my rule, and my n is where the domain number goes, and we always start with the number 1, okay, for your domain. Now, once you have a sequence, you can also do a summation of a sequence, which means you're adding up all those terms. So it says when the terms of a sequence are added together, the resulting expression is a series. So we have the difference here between a series where you're adding the terms together and a sequence where you're just listing them. Okay, so a sequence, you're just listing the terms. A series, you're adding them together. And on a series, we have summation notation or sigma notation. This right here is the Greek letter sigma. Okay, if you look up a Greek alphabet, that's the Greek letter sigma, and it means sum. Okay, so we use it to add up the terms of a sequence. So in a summation notation or sigma notation, we have an index. Okay, I is the index, you see that here. Okay, so we've got this sigma notation, I equals 1 up to 4 to I. So on this one, actually we can use this, I didn't even realize it when I came up with the rule over here. So if we have sigma of 2I and I goes from 1 to 4, what that means is if we're gonna use this index, let me first say that this is the lower limit, and the 4 up here is the upper limit. So what that essentially is telling us is it's limiting this series to just 4 terms that we're then going to add. Okay, so this is going to be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, and then we're actually going to get an answer here. So 2 plus 4 plus 6 plus 8. Okay, and I like to do easy math here in pairs. 2 and 8 gives me 10. 4 and 6 gives me 10. So obviously the answer to that summation is 20. Okay, so that's a summation of a series, or we can just have a sequence of numbers. Okay, ooh, not really sure what happened there. So summation of a series or a sequence of numbers. So this is sequence. This is summation of series. I'm not sure what's happening here with my Smart Ink. Okay, I'm back. The Smart Ink is working again. Okay, so sequence, just listing the numbers of a pattern, and series, we're summing them. We're adding them all up. Okay, so let's look down here, right terms of sequences. So these are the rules, okay? This right here is the rule, all right? This right here is the rule, and it tells us how to get from one term to the next. And remember, no domain is specified. You begin with n equals 1, almost always. Okay, very rarely do you begin with anything other than 1. And if you ever do, they're going to show that to you. They're going to tell you. So this one, notice, we're using this rule over here. So we're putting in, here's our domain. We got the 1, 2, 3, and keep going. Okay, and they wanted 6 terms. So that's why we go 4, 5, 6. So here is our sequence. Okay. Now, over here, again, this rule goes with these. Okay, and notice where your n is. That starts with your 1 and goes up to 6. That's where you put in your numbers. 1 through 6 is where the n is. Okay, and again, all you're doing is oscillating between +1 and -1. So let's do these down here together in the example. So write the first 6 terms of the sequence. So number 1, okay, let me see if I can squeeze them over here. Number 1, a to the n, that's just generic for the nth term, the first term, the second term, the third term. So a sub 1, that's the first term, is 1 minus 2. A sub 2 is 2 minus 2. A sub 3 is 3 minus 2. A sub 4 is 4 minus 2. A sub 5 is 5 minus 2. A sub 6 is 6 minus 2. So these would give me my sequence of numbers for the first 6 terms. Okay, that's number 1. I'm not going to do all of these. Let's do number 3. So let's do number 3. I'll do it over here. So number 3, we have a to the n, or a sub n, I should say, equals 2 to the n. Now, I want to do this one because this one's pretty common. Okay, so I want you to be able to kind of recognize what this does to the numbers here. So this tells me that the first term is 2 to the first power. The second term of the sequence is 2 to the second power. The third term of the sequence is 2 cubed. Fourth term is 2 to the fourth. Fifth term is 2 to the fifth. Sixth term is 2 to the sixth. So this gives me 2, 4, 8, 16, 32, 64. These are the first 6 terms of the sequence. Notice it is doubling. Okay, so anytime you've got a pattern of doubling, okay, you are going to have a base of 2 to a power. Okay, now we usually have to kind of see where the starting point is to know what to do with our n to get the right number to start with. But anytime you are doubling your number, you're going to have a base 2 to some power with n in it. Okay, and number 4, let me see if I can do it here off to the side. I may not do all 6 terms, but this number 4, I would have -1 to the first over 1. Then I would have -1 squared over 2. Then I would have -1 cubed over 3, and so on. So this would just give me -1, right? This one, -1 squared, is +1. This would give me 1/2. This would give me -1/3. If I did -1 to the 4th over 4, I would get +1/4. So these, I just did to 4, not 6. But notice that my numerator is always going to stay a 1. My denominator is going to increase by 1 because that's your index number, if you will, your n. And then my signs are going to alternate because I've got a -1 as the base. Okay, so now if we're given a sequence, can we find the rule? Okay, so it says here on example 2, describe the pattern, write the next term, and write a rule for the nth term of the sequence 2, 6, 12, 20. So at first I thought, oh, 6 to 12, you know, that's doubling, but that doesn't hold true. So what I like to do here is think of different things. First of all, this has a difference of 4. This has a difference of 6. This has a difference of 8. So I add 4, add 6, add 8. So if you look at the rule here, again, what you need to keep in mind is this input. Okay, this, remember, is your domain, your input. You've got to have a number in your rule that uses a 1, then 2, then 3, then 4, then 5, because your input is going to go up by 1 each time. So you have to have those numbers in it. Well, then if you look, you're just taking 1 times 2 to get the first one, 2 times 3 to get the next one, 3 times 4 to get 12, 4 times 5 to get 20. So this would be the rule for the nth term. The reason why we use the n, it's kind of like the index, it's just the generic one. Okay, so if you wanted to find the 10th term of sequence, and there are problems like this all over the ACT test, the 10th term of a sequence, that would be a sub 10 equals 10 times 10 plus 1. So 10 times 11 is 110. So you wouldn't necessarily have to go and find, if you were looking for the 10th term, once you found the rule, you wouldn't have to find the 9 preceding it. You could just use the rule. Okay, it's a time saver. So definitely useful on the ACT test. So let's look at some more exercises here. So for the sequence, describe the pattern, write the next term, and write the rule. I'm not real big on describing the pattern. You can, I don't know. So this one, again, remember, we have to use our index. We have to use a 1. We have to use a 2 to get this one, a 3 to get this one, a 4 to get this one, and so on. So then do you see some kind of rule for how we get a 3 using the number 1? Well, it's going to be times 3. We get to 6 using the number 2 times 3. 3 to get to 9 times 3. 4 to get to 12 times 3. So that's our rule. So our rule is the nth term is going to be n times 3, or 3n. Okay, that's our rule. And then it says in, write the next term. Of course, the next term would be a 15, right? 3 times 5. So here's our rule. Here's our next term is 15. That would be what I'd be looking for. Okay, so over here, let's look at number 6. Number 6, notice our next one is going to have a 1 on top. They all have a 1 on top. Okay, and then we go from 1 to 3 to 5 to 7. The next one's going to have to be 9, right? So that would be our next term. But then again, how do we get from one term to the next? Well, I've got to use the index numbers, the 1, the 2, the 3. So how do I get from a 1 to get to 1? How do I get from a 2 to get to 3? How do I get from a 3 to get to 5? How do I get from a 4 to get to 7? Okay, well, 1 is just 1. 2 plus 1 is 3. 3 plus 2 is 5. 4 plus 3 is 7. But I have no way to increase by 1 each time. So this actually ends up being a sub n, the nth term, is 1 over 2n minus 1. Okay, now think about this. If I take 1 times 2, I get 2. Minus 1 gives me the 1. 2 times 2 is 4, minus 1 is 3. 3 times 2 is 6, minus 1 is 5. 4 times 2 is 8, minus 1 is 7, and so on. Okay, so that's my rule there. Let's look at number 7. Number 7, okay, we're essentially adding 1 each time. So that means that our next term is going to be a 0, correct? But what's the rule? I got to write the rule. So how do I get from a 1 to a negative 4? How do I get from a 2 to a negative 3? How do I get from a 3 to a negative 2? From a 4 to a negative 1? Well, the only thing I can see here is we're subtracting 5, right? So that's going to be our rule. The nth term is going to be n minus 5. So again, if I wanted the 10th term, 10 minus 5 is 5. If I wanted the 100th term, and again, those are the kind that I see on ACT tests all the time. It's 100 minus 5, or 95. Okay, the next one. This one I think maybe is a little easier to see. Obviously on top we are counting up by 1, so the next fraction is going to be a 6. On the bottom we're also counting up by 1, but we started at a different number. So this is going to be 7. So 6/7 is going to be my next term of the sequence. And this one, again, remember, we are trying to use the number 1. How do I get from the number 1 to a 2 on top and a 3 on bottom? How do I get from the number 2 to a 3 on top and a 4 on bottom? How do I get from the number 3 to a 4 on top and a 5 on bottom? Well, if you look, you add 1 on the top and 2 on the bottom. So that's what we do. N plus 1 over n plus 2. That's my rule. Okay? So you have to look at these in terms of the number of term, or your index. For the first term, you've got to use a 1 in that calculation. For the second term, you've got to use a 2 in that calculation, and so on. Now, series says write the series using summation notation. Now remember the difference between a series and a sequence. A sequence, we're literally just listing the numbers in order. A series, we are summing them, we're adding them all up. So they give us the answers here, the solutions to A and B, but we are going, once again, we have to find the rule, right? So how do I get from a 1 and I stay a 1 here? How do I get a 2 and get to 4? How do I use a 3 and get to 9? How do I use a 4 and get to 16? Well, to me, it looks like we're squaring, right? So this is 1 squared. This is 2 squared. This is 3 squared. This is 4 squared. So notice down here, that's my rule. Now they're using an I instead of an N. It really doesn't matter what you use. But they've got this summation notation here, okay? And they're starting you notice down here your lower limit, they're starting with I equals 1. You've got to have a starting point, and typically it is a 1, but it doesn't have to be. You can actually start with whatever number you pick, but you certainly have to name it, okay? And then this one, notice the dot, dot, dot. This is an infinite series, okay? There's no end point. So infinite series go up to infinity, okay? So you're essentially adding them all up. And in a later section, we're going to talk about how we actually find the sum of that. So if possible, how we can get to the limit of that. So part B here, again, we got to find the rule, okay? And this one, if you notice, is very similar. This part B is very similar to this number 8, okay? So how do we use the number 1? How do we use the number 1 and get to a 1 on top and a 3 on bottom? How do we use the number 2 and get to a 2 on top and a 4 on bottom? How do we use the number 3 and get to a 3 on top and a 5 on bottom? Okay, well, if you notice here, the 1 matches the top, the 2 matches the top, the 3 matches the top, but on bottom, it looks like you're adding 2 to each one. So if you look, that is the rule. Here's the rule right here. A sub I equals I over I plus 2. Okay, and here's the deal though. This is a finite because it has an end point. It ends. So it's a finite series. So when we go to write the summation notation, notice we use the rule over here on the right. Okay, we've got our starting point, I equals 1, and then that's our lower limit. Our upper limit is 9. There is a distinct starting and stopping point. Okay, so we need the rule, we need the starting point, we need the stopping point. So let's look at some of these exercises, see if we can figure them out. Okay, so again, first thing we've got to do here is find the rule. So on number 9, I've got to use the number 1 and get to 5. The number 2 has to get me to 6. The number 3 has to get me to 7, somehow, some way. Blah, 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 blah. And this is a finite series. Okay, so what's the rule? If you just look here, it looks like the rule is plus 4, doesn't it? 2 plus 4 is 6. 3 plus 4 is 7. 1 plus 4 is 5. So that seems to be the rule. So my summation notation would look like this. My rule then is I or N or K. It really makes no difference what letter you choose as long as you're consistent. So it's going to be I plus 4. Our I is going to start with 1. And then our end point, where do we end up? What I would give me a 12? Well, the I that would give me the 12 would have to be 8. So our upper limit is 8. So that's number 9. Okay. Now, 10, you notice, is an infinite series. So right off the bat, I know that the upper limit is going to be infinity. Okay. Now, once again, I have to find the rule. So how do I get from a 1 to a 4? How do I get from a 2 to an 8? How do I get from a 3 to a 12? Well, you can see there that in all 3 of those cases, if I just multiply by 4, right, I get the desired number. So this is going to be 4i or 4n or 4k. I don't really care what you use. And we're going to start with 1 and go to infinity. Okay, because that is an infinite series. Number 11. Once again, I have to find the rule. Okay, so how do I use the number 1 and get a 1 on top and a 3 on bottom? How do I use the number 2 and get a 2 on top and a 4 on bottom? How do I use the number 3 and get a 3 on top and a 5 on bottom? Well, obviously the rule is just going to be I on top, right? Or N or K, again, whatever letter you want to use, I don't care. And then how do we get the number on bottom? It looks like we add 2 each time, right? So this is going to be I plus 2. That's my rule. Now, Summation notation, got to write the sigma. My I is going to start with 1, but where does my I end? Well, if my I is my top number, then obviously my fraction ends here with 12. So I'm going to go from 1 to 12. My lower limit is a 1, upper limit is 12, and I've got the rule beside the sigma. Okay. Now, this next one, last one. Again, got to find the rule. Okay. So how do I get from 1 to 3? How do I get from 2 to 5? How do I get from 3 to 6? So if I'm thinking, okay, 2 times 1 plus 1. Well, 2 times 1 plus 1 gives me 3. 2 times 1, or 2 times 2 plus 1 gets me 5. And 2 times 6 plus 1 gets me 7. So I think I hit it right off the bat. Because it can't be plus 2, because 1 plus 2 is 3, but 2 plus 2 is not 5. So the rule then is going to be 2i plus 1. That's the rule. And since it's a binomial, we usually put the binomial rules in parentheses so that we know that the sigma notation here applies to the whole thing. And then our starting point is, of course, a 1. And then because of the dot, 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 this again is going to be the upper limit of infinity. Okay? So again, when you're trying to find the rule, think of it in terms of the index number, the first term, the second term. How do I use a 1? How do I use a 2? How do I use a 3? Okay? All right, so that is the study guide. Let's do some practice problems. Okay, practice problems. Write the first 6 terms of the sequence. Again, all you're doing is plugging in. Okay, I'm going to do number 4 here. So first 6 terms of the sequence. Now notice they wrote this one in terms of like a function notation. Okay, whether you write it this way or whether you write it this way, it's the same thing. So on number 4, first 6 terms of the sequence, f of 1 is going to equal 1 squared plus 3. F of 2 equals 2 squared plus 3. F of 3 equals 3 squared plus 3. F of 4 equals 4 squared plus 3. F of 5 is 5 squared plus 3. And f of 6 is, of course, 6 squared plus 3. Okay? You can poke all those in calculators or whatever. This is going to give you a 4. 4 plus 3 is 7. 9 plus 3 is 12. 16 plus 3 is 19. 25 plus 3, I know I'm running out of room here. 28, excuse me. 6 squared plus 3, so 36 plus 3 is 39. So this would give me my first 6 terms of the sequence. I hope you can see that over top of the writing. So that's all you're doing, is just, again, changing the N or the I or the K or whatever letter they happen to use, starting with the number 1 and going up. Okay? All right, the next part here says, for the sequence, describe the pattern, write the next term, and write a rule for the nth term. So actually, let's look at number 9. Okay, so I am looking at number 9, and I'm asking myself, how do I use the number 1 to get to a negative 3? And then how do I use the number 2 and get to a 6? How do I use the number 3 and get to a negative 9? How do I use the number 4 and get to a 12? Well, if we ignore the fact that our signs are changing, it looks to me that we are multiplying by 3. 1 times 3 gets me negative 3. 2 times 3 gets me 6. 3 times 3 gets me 9. 4 times 3 gets me 12. But there's one other thing. Anytime your signs oscillate from negative to positive, you are going to have something with a negative 1 to some power. So in this case, I'm going to put negative 1 to the nth. okay, that's going to change the sign, and it's going to make the first one a negative one. And then it's going to be 3 times n for the rest of the rule, right? So let's try it out. Once we think we have the rule, plug in a couple and see if you get the right number. So -1 to the first power, okay, let me put it over here. -1 to the first power times 3 times 1. Okay, that is a -1 times 3 gives me -3. -1 squared times 3 times 2. -1 squared is +1 times 6 is just 6. -1 cubed times 3 times 3 gives me -9, and so on. That's going to work. So that's my rule. So this is my a sub n equals. That's my rule. Okay, and they wanted the next term. What would be the next term of the sequence after 12? It would have to be a -15. Okay, so a -15 would be the next term, and then my rule would be that. Now, let's do number 13. 13, the first thing that jumped out at me on 13 was the difference here on each of these is 1.1. You see that? So then how do I use that difference and then get to my first number? Because I have to use the number 1 to get to the -0.9. I have to use the number 2 to get to the 0.2. I have to use the number 3 to get to 1.3 and so on. So anytime you have a difference that's constant between terms, you are going to take that difference and multiply it by the index and then do something with it. So I know somewhere along the line, I'm going to end up with a 1.1n. Anytime my difference stays constant, that's going to tell me that I'm going to have a 1.1 times n. Now, I have to figure out my starting point. So if my n starts at 1, 1.1 times 1 is 1.1. Well, how do I get from 1.1 to a -0.9? Well, I'm going to have to subtract 2 from it. Now, let's check that out and see if it works for the next one. So what if I have 1.1 times 2 minus 2? Do I get the second term? Well, this would be 2.2 minus 2. Sure enough, that would give me 0.2. Well, try it on the next one. Put in a 3. Okay, 1.1 times 3 is 3.3. Minus 2 is 1.3. So that works. So that's my rule. Okay, so there's my rule. And then what would be my next term? If I'm adding 1.1 each time, obviously my next term would be 3.5. Okay. All right. I hope that helps. Now, the next part, graph the sequence. Okay, think of this in terms of ordered pairs. So this, remember, came from a domain of 1. This number came from a domain of 2. This one from 3, this one from 4, this one from 5. So actually, let me change colors here. So my ordered pairs are going to be a 1, -6. The number 2 is where I got a -4. The number 3 is where I got a -2. The number 4 is where I got 0. The number 5 is where I got 2. So your domain will always be sequential numbers, okay? Remember, your domain will always be sequential numbers, and unless they tell you otherwise, it should always start with 1. So a 1, -6 looks like it would be here, and we're literally just graphing points. Okay, 2, -4. It looks like the boxes we're counting by 2's there. 3, -2. 4, 0. 5, 2. So you're not connecting the dots, you're literally just plotting the points. Okay, that's it. Now, write the series using summation notation. Okay, write the series using summation notation. So first we got to find the rule. Okay, so again, how do I get from a 1 to a 10, from a 2 to a 20, from a 3 to a 30? Well, I think it's pretty obvious. We're going to be multiplying by 10, right? So my rule then is going to be 10i or 10n or 10k, whatever you want to use it, I don't care. And then we got to have a starting point and a stopping point. My starting point is, of course, a 1. I should put I equals 1, sorry. And then my stopping point, we got all the way up to 50. This is a finite series. So this would be 5 times 10. So my stopping point is a 5. Okay? Now, that's all you have to do on those. Let's look at, actually I want to do 19 with you. Actually, I want to do 20 with you guys. 19 isn't bad either, but let's do 20. Remember, let me just point out on 19 that your signs oscillate from positive to negative, so you are going to have a -1 to some power. Okay, and then you're going to have to figure out the rest of the rule. But anytime your signs oscillate, positive, negative, you're going to have -1 to some power. Okay, so let's look at 20. Now 20 is another one that when I look at it, it looks like my difference on all of these is a -14. Well, do you all remember what I said up above when we had a constant difference, like on number 13 here, we had a constant difference of 1.1. So in my rule, I end up with a 1.1 times n. Same thing here on 20. If my constant difference is a -14, somewhere along the line, I'm going to have -14. And I used n instead of I. It doesn't matter as long as you're consistent. So now, I know there's going to be a -14n somewhere in my rule, but how do I get from a -14, what do I do with that, or what do I add to that to get to 15? Because remember, I'm using the number 1 here, and this uses the number 2, and this term uses the number 3, and this term uses the number 4, and so on and so forth. Okay, and first of all, I guess I could go ahead. I know this is going to be a summation. It's going to start at 1, it's going to end at 4, right? Because I only have 4 terms. And then I've got to do something to that -14n. Well, if my n is 1 and I get -14, what would I have to add to that to end up with a 15 to start? Well, it's going to be 29, because 29 minus 14 is 15. So this would be your summation notation. Okay? Now, check yourself and see if it works on all of them. Okay? Let's actually check and see if that rule works like on the third one. So 29 minus 14 times 3. Well, that is 29. 14 times 3 is 42. Okay, so 29 minus 42 is definitely a -13. It works. Okay, so I always test my rule on just one of the numbers in the series or sequence just to see if it works. Okay, now remember this one in the middle, the one that I didn't do, just a reminder, that is an infinite, so you're going to have infinity up here. If you used k or I or whatever, you're going to start at 1 and end at infinity, and then you got to find the rule. Okay. All right, 21 through 23, find the sum of the series. So you're literally just poking in the numbers and finding the sum. I think these are pretty straightforward. Keep in mind, though, I want to point out, this one starts at a 2, okay, not a 1. So you do have to, you know, be on guard here. This one, you are finding 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So 1 plus 4 plus 9 plus 16 plus 25 and so on. Okay? So this is 10, this is 20, so that's 30 plus 25 is 55. That should be that answer. Okay, so that's what you're doing on those, is you're literally just using the rule and using your starting point and ending point to finish it. Okay, last one. Just kind of wanted to talk you through this. I'm going to do all of them. So it says a petri dish contains 3 amoebas. An amoeba is a microorganism that reproduces using the process of fission. by simply dividing itself into 2 smaller amoebas. Once the new amoebas mature, they will go through the same process. So write the terms of the sequence describing the first 4 generations of the amoeba in the Petri dish. So it says we started with 3 amoebas, right? So 3, and then they split and give you 6. Those split into 2 and make 12. Those split into 2 and make 24. That would be the first 4 generations. You're just essentially doubling, right? Well, now I don't know if you all remember, but I said earlier, when you double something, you're going to have a base of 2 to some power. I know that's got to be in the rule. Anytime you double your quantity. So I'm going to have a to the n, or a sub n, the nth term, is going to have something to do with 2 to some power. Now, I don't know if it's just going to be 2 to the n or 2 to the n minus 1 or 2 whatever. I don't know. Okay. So how can I solve this? How can I figure out? I know that 2 to the n has to be in there somewhere. How can I use a 1 here and get to 3? How can I use a 2 and get to 6? How can I use a 3 and get to 4? And a 4 and get to 24, and so on and so forth. So I have to kind of figure this out. So if I just have 2 to the n, that's 2 to the first, that's 2. So I could add 1, that gives me 3. So does that work? If I put a plus 1 back here. Well, let's check it out for the next one. Is 6 2 squared plus 1? Well, 2 squared is 4, plus 1 is 5. Nope, that doesn't work. So I know 2 to the n has to be in there somewhere. But that ain't working this time. Now, what if I have 2 to the n minus 1? Okay, 2 to the n minus 1 means my first term would be, well, first term, 1 minus 1 would be 0. 2 to the 0 power is a positive 1. So then a 1 times 3 maybe? So maybe this times 3, does that work? So let's try it out. Let's try it out on the third term. So if we're going to test that out, so then the third term would be 3 times 2 to the 3 minus 1. So this would be 3 times 2 squared, which would be 3 times 4, which is 12. That works. Let's try it on the fourth term. A sub 4 would be 3 times 2 to the 4 minus 1. Well, that would be 3 times 2 cubed. That would be 3 times 8, which is 24. Yep, that works. I think that's my rule. Okay, so this is my rule here. Again, some of these, I wish there was a better process, but you just kind of have to play with it. Now, find the 10th term of the sequence and describe in words what this term represents. The 10th term of the sequence. I don't have to go up here to part A and carry on with the 5th, the 6th, the 7th, the 8th, the 9th term. I can use my rule. So my rule tells me that A sub 10 would be 3 times 2 to the 10 minus 1, or 3 times 2 to the 9th power. Literally, you poke that in a calculator and you get 1,536. So the 10th term would give you that, and then what that term represents. That's the 10th generation. If each generation, it splits in doubles, then that's the 10th generation. Okay? All right, this concludes the lecture for section 7.1. I will have the links to the homework and stuff posted. Thanks, guys.